One of the joys of doing research is communicating with other researchers, and I had great fun for a number of hours this morning finding out what's going on here and commenting on it. And now we've turned the tables. I'm going to try out some new ideas on you and would very much like your feedback. What I want to talk about, of course, is energy. And let me start by noting that we have big national and global problems in energy. And you might find it interesting to hear how I talk about it when I talk to a US audience in terms of what the challenges are. The first has got to do with energy security. And in the US, it's mostly about oil. And because oil is used in the US almost exclusively for transportation, this is about the price of petrol and diesel fuel in the US. That price is currently high and it is volatile, and that does very disturbing things to the US economically. That's also complicated by the fact that the easy oil resources are concentrated in the hands increasingly of a few countries whose fates and actions are not clear to us. And as this graph shows, only a very small fraction of the conventional reserves can be accessed by the international oil companies. It's the national oil companies, Saudi Aramco, PDVSA, Petrobras, and so on, who are holding most of the conventional reserves. The second issue, energy in the US, is competitiveness. The US, even though it invented lithium-ion technology, is responsible only for a small fraction of the manufacturing today. The same is true in photovoltaics, small fraction of the world's manufacturing. And I can tell you the same story about many other energy technologies: wind, nuclear technology, fuel-efficient automobiles, although that's changing somewhat, et cetera, et cetera. So the second issue is competitiveness. The third issue is environmental concerns, most problematically the growing greenhouse gas concentrations in the atmosphere and the growing emissions, largely due to development in the developing countries, but also in the US water. The fastest growing parts of the US are some of the driest, Nevada, Arizona, and that has severe implications for how we generate electricity in those regions. Technology development is often seen as the solution to many of these problems. And when I was sitting in the Department of Energy in the stationary sector, we were supporting R&D and initial deployment in solar, geothermal, fusion, the smart grid, smart meters. One can go on and on. In transportation, biofuels, electric vehicles, etc. And you would often hear the phrases like moonshot, Manhattan Project, inventing the clean energy future, and so on. Great discussion by politicians. Scientists also adopt these phrases. My own belief is that this is not how energy really works. There are structural features in the real energy system that slow down or even prevent the impact of technology change. And transformation has in fact not happened at the pace required by either the security or environmental or competitiveness drivers that we have. I like to show this picture to illustrate the pace of change. It shows the US energy supply for the last 160 years. And you can see back at the time of the Civil War in the US in 1850, most of the country's energy came from wood. And as we went on through the 19th century, coal became more important due to the Industrial Revolution. Oil became important due to mobility, natural gas, a little bit of nuclear energy in the last several decades, and then an even tinier bit of renewables, wind and solar, in the last few decades. Again, 1 bar per decade in this chart. We get fooled sometimes in thinking about energy technologies by the great revolution we've been experiencing in biomedical and information technologies. And here in this chart, I've taken the last decade and blown it up for personal audio and video equipment since the year 2000. And you can see that there's been an entire shift from personal CDs at the turn of the century. Nobody even remembers what those are, perhaps. And now, of course, flash and MP3 players. This has happened in a decade. This has taken a century. The good news is that the energy technologies do change. They change in response to economics, to technology development, to regulation, to politics. But the bad news is, as you see, it takes decades to make a material change, at least on the supply side. There are reasons for that are fundamental to energy. They've got to do with the energy scale, the fact that, by and large, these are very large facilities, power plants, refineries, and so on. They cost a lot of money. They live for a long time, 50, 60, 70 years. Even automobiles live for 15 years or more. There's a lot of money tied up in these pieces of hardware, and society does not easily change that over. Also important is the fact that electrical power or fuels for transportation are commodities. The consumer cannot tell the difference where those things come from. And so the companies that supply them, whether it's the utilities or the oil companies, are competing with one another on very thin cost margins. And when the profit margins are so small, companies are reluctant to take technology chances in big facilities. You have many other levers you can pull besides technology to make money. And then finally, there's the obvious issue of incumbency. Businesses that are making lots of money in energy really don't want to see the technologies change very rapidly. So for all those reasons, technology has not been the savior that I think many of us would have liked it to be. In the end, it's not only about inventing the new technologies, but it's about the deployment of them. How many quads of energy did you save or produce? How many barrels of oil did you displace? How many tons of CO2 did you mitigate? These are the real-world impacts, which is, after all, why we're doing all of this. It's not just about getting the technology to work. And when you think about it in those terms, the societal levers are as important and maybe more important than the technology alone. Regulation, economics, behavior, perceptions. Those are things that influence the operation of existing technologies, leaving the lights on, driving, etc., as well as the introduction of new technologies. And they're different then, but not independent of the technology development itself. We, of course, as scientists and engineers, are focusing on the technology, but it's these other things that are really the rate-limiting steps, almost always. Energy changes involve people, and the U.S. has, in fact, had mixed success in fusing the societal and technical aspects together to be effective. We have renewable fuels and renewable power standards in the U.S. in various ways. A certain fraction of electricity shall come from renewable sources. A certain fraction of fuels shall be biofuels. They've had mixed success. In some cases, the targets have been met. In other cases, the politicians have had too much aspiration, let me put it that way. Another good example is the integrated gasification combined cycle technology, IGCC, that the government helped develop and demonstrate in the mid-90s or so. Wonderful technical success. Everyone thought that it would be a great game changer in the power sector. To date, 15 years after the first demonstration, there's still exactly one IGCC plant running in the U.S. Vehicle fuel economy standards in the U.S., miles per gallon, the so-called CAFE standards, are in fact a useful regulatory mechanism that is improving vehicle efficiency and decreasing oil use. And in fact, the Obama administration aggressively pushed these standards forward. appliances and building standards have also been pretty effective things at the intersection of technology and society. Pricing externalities, particularly putting a price on carbon, has not been yet a success in the US, and I have to say, frankly, the prospects for the next several election cycles don't look very good for that politically. So the question is, how do people and organizations think about, behave as they use energy, whether it's the use of existing technologies or the introduction of new technologies? And there is, at the moment, no place in the US government where these things come together. The Department of Energy is largely about technology development, a little bit about regulation. The National Science Foundation has the brief to study societal issues, social sciences, but is not an applied agency in the way you would like to bring together to solve these problems. So I got involved with this now almost a year ago, perhaps more, when the American Academy of Arts and Sciences convened a conference and a working group on how can we better bring the social sciences to bear on energy matters. And there is a report that was put out. I would urge you, if you're interested, to have a look at it. The link is up there. That talks about the different social science aspects that need to be done in order to make energy policy more effective. And so we've been thinking about this for a while. There are some interesting societal questions one can ask. How do people perceive new technologies, and what makes them willing or unwilling to adopt it? How can policies be made more durable? Because the timescales to change the energy system are decades, you need policies that need to be consistent on those same timescales. And how do we do that in a political sense? What are the best practices for incentives? I know that there's been experience here with incentives for solar power, for example, that are both good and bad in terms of their outcomes. Trust. With so many different voices in energy, who do you really trust to tell you something factual? Risk. How do people perceive risk? Energy awareness, behavior and energy modeling. Can we quantify rebound? This is the notion that the benefits of efficiency are not always fully captured. How do we put value as a society on intangibles like human life, intergenerational equity, and so on? These are wonderful questions, all of which enter into energy discussions in one way or another. Well, people have been doing social science for decades, and you might ask, what new can you bring to the subject? And I and two colleagues working at the Institute for Defense Analysis, Science and Technology Policy Institute, Sally Keller and Stephanie Shipp, both of whom are statisticians by training, have come to understand that there is an opportunity with the way the social sciences are going to start to address some of these questions, largely through what's called big data. And big data, in fact, can be brought to bear on societal questions. We, as a society, are getting much better at sensing, transmitting, storing, and analyzing big data, large data flows for both physical and societal data. And every one of today's global challenges, including energy, can benefit enormously by capitalizing on this big data revolution. Collecting and integrating big data streams, understanding the fundamental phenomena through those data, and then using that understanding to better operate the complex systems or to guide policy. There's a very nice quote from Hal Varian, who is a noted statistician, and he said, I keep saying that the sexy job in the next 10 years will be statisticians. All right. I'll just read you through the quote. The ability to take data, to understand it, process it, extract value from it, visualize it, communicate it is going to be a hugely important skill in the next decades, not only at the professional level, but at the educational level. And it's probably worth reading Hal's bit from that. It is part of the zeitgeist in both the society and in the sciences. If you look at social science, as I have done now as an outsider, what you see is that the data tradition is either surveys in which you go out and ask 1,000 people what they think, or you do experiments, again on about 1,000 people, or you do large-scale aggregated statistical data flows, like the economic statistics or the census in the US. These are clean, well-controlled experiments, but they're limited in scale and or their resolution. In other parts of science, there's a different data collection methodology, and that is you ingest enormous amounts of organic data flows that are there already. You rely on high statistics, you do empirical corrections to the data, and you can gain understanding. And one of the great examples of how big data has come in and revolutionized science is in astronomy. For example, the Sloan Digital Sky Survey. For those of you who are not astronomers, I'll just tell you that about 20 years ago, several astronomers, most notably Jim Gunn at Princeton, realized that instead of the traditional paradigm where an astronomer got 2 nights on a telescope every year and used those to look at a couple of objects, you could instead build an automated system that systematically took pictures of the sky, cataloged them, and then made all of that data available to many astronomers. And the Digital Sky Survey started working about 20 years ago, collected, as you see, about 100 billion rows of data, galaxies, spectra, and so on from an automated telescope in Arizona. And there was science that came out. It used to be that when you studied supernovae, you could count them on one hand every year. They were labeled A, B, C, and D in 1987, 88, and so on. What the Sky Survey allowed people to do was to get of order 500 supernovae, characterize their spectra. This is a picture of every one that they found, and do a great deal of science and systematics within it. So suddenly astronomy turned from, if you'll excuse me, stamp collecting into a serious statistical science. That's grown up since. We now have the National Virtual Observatory, which is part of an international alliance. And you have folks from all over the world feeding these enormous databases in which you can then do a kind of science that people never imagined 20 years ago. Other sciences are also creating observatories. This particular set of pictures is from NEON, a US effort, which is the National Ecological Observatory Network, which is to collect lots of data on many different ecological sites through in situ sensors, airborne satellites, and so on. Put it all together and see what you can understand. Here's another one that Europe is involved with in aerosol research. There are also now, so far that's been physical data, there are very many social data streams already out there on the web. Those of you who may not know about the Billion Price project at MIT worth mentioning, there was a guy at MIT, I think he was from Argentina, but I don't hold me to that, who started to look at the cost of living figures that the Argentine government was putting out, and he said that's not right. And he started to scour the web for prices of various goods in Argentina and compiled his own consumer price index. That made the Argentine government pretty mad, actually. But then he started to do it worldwide. And so there are engines now that go out and scour the web for prices and can give you a real cost of living index in real time, once a day, for many different economies. And there are all kinds of interesting fluctuations in those indices that are correlated with news events and so on. So that's one way in which you can tap into social data. Google is starting to put lots of public data out on the web, and as I mentioned, the statisticians are starting to understand how to deal with this. So, you know, you're left with the question then as a scientist, not a social scientist, if you can know anything about society, what do you want to know in order to address a problem? And asking that question of the social scientists sort of gets their attention because they've never thought about their science in that way. So let me now refine the question a little bit and ask, suppose you could fully instrument a city. Why a city? Because you want to go where the people are. Half the world's population now lives in large cities. Within 20 or 30 years, it's going to be 75%. So suppose you could create an urban observatory with the goal of understanding a city in the same way that we're trying to understand a cell, for example, in terms of all the processes that are going on. So you'd like to fuse socioeconomic data and physical data about the city. What data flows? How large would they be? What could you do with such data? How would you acquire such data? These are all questions that people are starting to think about in various ways. This is a reference to a nice article by Sandy Pentland in Technology Review, Society's Nervous System, Building Effective Government, Energy, and Public Health Systems by putting this nervous system into society, sensing, understanding, modeling what's going on. Before anybody else says it, I'll say the word privacy, a very important discussion here. I will come back to that in a few slides. Let's put it aside for the moment, but it is extraordinarily important. Data rates first. Physicists, you always start by, well, how big is the problem? What am I trying to do? You can kind of do these order of magnitude estimates for fun. There are 3 million people inside 10 kilometers in a dense urban environment. 10 to the 4th per square kilometer is a dense urban population. They live in 1 million households, work in about 1/3 of a million businesses. There are about 500,000 vehicles, let's say. Data rates, personal data. If I wanted to collect everything about people, know their position, physiology, psychology, I'd probably 20 bytes updated every 5 seconds. That's 12 megabytes a second. Transactional data, economics, communications, far less. Total, something like 20 megabytes a second. Over a year, 600 terabytes. Doesn't cost much to store that at all. So we're not talking about enormous data rates on the scale of what we handle in the sciences. What could the data flows be? What might you tap into? Societal data, first of all, by administrative records or surveys. So there are census, there are building permits, there are transactions, economics, there are communications, personal data, locations, physiology, operational data, traffic, transit, the utility systems, the health system, and so on. And then there's physical data, either through in situ sensors or remote sensors, resolutions to be determined. We'll come back to that in a moment. Imagery, obviously, optical and infrared. The radio frequency spectrum in a city, the magnetic spectrum should be very rich. The environmental data, meteorological, seismic, acoustic, you can go on and list your favorite things to go measure. Here's some examples, just thinking a little bit out of the box. You can buy a personal activity monitor, and it's a band on your wrist that monitors acceleration, pulse, skin resistance, and so on. It talks to your smartphone and then off to a grid somewhere. Surveillance cameras are proliferating, satellite overhead pictures. We have statistical data. This is a picture of the Census Bureau. And then you have big buildings in cities. From the top of a big building, you can see 1 million people at once. What can you do in a statistical way with that kind of data? The buildings are getting bigger and bigger. It's a pyramid all the way to the big building in Dubai. You can see a lot from a big building. Of course, there's shadowing. This particular graphic done with a geographical information system hypothetically puts the Eiffel Tower in the middle of downtown Boston and asks which areas in Boston can see either the top of the tower or the platform that's down at its base. And you can see you can start to cover with several vantage points a good fraction of the city. This is a picture of Manhattan taken in the infrared at night, and you can clearly see where the heat is coming out of the buildings. So you could start to get some sense of energy use. There are other examples. It's a good example, a company called O-Power, which takes utility data. You sign up with it. It shares your utility data anonymously with other people. And so, for example, you can say, my home, in this case, used 340 kilowatt hours. All homes, less efficient homes, even less than that. And so you can get this kind of peer-to-peer interaction, competition, if you like, to know who's most efficient or least efficient in energy. So what could you do with such data if you had it? You can start with simple things like optimizing operations. Obviously, traffic control, utility loads, and so on. The real-time things that the city has to do. You can do infrastructure planning a lot better than you're able to do. Where do I site the bus routes, the rail lines? How do I do zoning in a more efficient way? If I understand how people are actually using and living in the city. I can identify energy use outliers. If you're in the top 10 percentile of electricity use, for example, let's go out and send a letter and say, hey, you're in the top 10% compared to your peers. We can probably help you reduce those costs. Travel and intersection patterns seem like an interesting thing to look at. Epidemiology. Who's close to whom? Who got sick? If I was close to someone else and they got sick, that might be an interesting thing to know. I can do policy experiments by changing the policies in one region or another and watching what happens. Just a story, in the US, if you want to build a big new apartment building, before you get permission to build, you have to file a statement about the impact of those additional residents on the traffic patterns and prove that it doesn't become unmanageable. Of course, in order to do that, there are various models that people use. No one ever goes back 2 years after the building was built and asks whether the model was right or not. And clearly, if you had this kind of data, you could start to do that. Urban meteorology, leaks, plume dispersal, greenhouse gas emissions monitoring, et cetera, et cetera. Many things that one can imagine doing as you start to acquire more and more data about a city. And there's a good quote from Yogi Berra. I don't know if Yogi Berra means much in this audience. Famous baseball player who had a number of wonderful sayings. Anyway, okay. Okay, let me come back a little bit to the issue of privacy, which is very important in this discussion, and a couple of thoughts. First of all, the privacy issues are structural. You cannot evade them. Because if you talk about studying society, to get these societal factors right, you have to study people at some level. Part of the intrinsic aspects of this business. A second is that people will voluntarily give up their data if they can see a personal or societal benefit. Social networks work on that principle. There's a website called Volt Stats, for example, in which drivers of the Chevy Volt, which is a plug-in hybrid, getting of order 100 miles to the gallon, they give up access to their vehicle data, or they give access to this website, which then posts comparative statistics of who got the most miles per gallon, who filled up the least, most miles on a charge, and so on. And they do that in part because it's a competition, in part for the societal benefit. Similarly, if I could promise you access to where all the parking spaces were in a crowded city in real time, you might be willing to give me your location data. I think also norms and expectations of personal data are changing with generations. Certainly, as I talk to people in their late teens or early 20s, they have a very different attitude about their personal data than I do 40 years older than they are. There are also technical fixes to dealing with the privacy issue. Multi-level security classification of data. Here is one example. a data enclave that's used by some of the US statistical agencies, where you have limited access by researchers who have been appropriately vetted, yet it's possible for them to access the data and do the science they need to do with it. And another thought is that privacy is eroding in any event. And those of you who might read the New York Times, for example, they've been doing a more or less weekly set of articles on big data and the way in which the private sector, the retailers, companies like Amazon, Google, Target, are using data about their customers in order to do their business better. So this is happening anyway, and my sense is that we should do our best to ensure that it's done sensibly. And then finally, we don't know yet what the optimal level of privacy is in order to do the kinds of things I've been talking about. And clearly, as we go in resolution from data about an individual home to a building, to an urban block, to a neighborhood, the anonymity goes up, but the volume of data and the ability to stratify goes down, to do correlations, and there's probably a sweet spot somewhere in the middle here, depending on application, that we just haven't yet figured out. So where do we go from here now, given these thoughts? There are certainly initiatives now that are looking at data access and generating pieces of social data. There is something going on in Maryland, the Population Research Center, future observatories in the social sciences. There's the American Academy report that I mentioned, and then there's some NSF work changing the conduct of science in the information age. This is happening already. The challenge here in part is bridging multiple disciplines. And it ranges everything from how do you sense and collect this data, how do you put it all together, how do you model, how do you get the social scientists to ask the right questions, how do you bring in the people who operate urban systems, do urban policy and planning in order to try to fully exploit what one can learn from this data. I think also what we need are specific projects that starts to combine multiple data streams, physical and tabular, together with validated modeling and can start to demonstrate real impacts. And there are two that stand out for me already in this regard. One has got to do with predictive policing in New York City. New York City has had a lot of success in using models to predict on a statistical sense what the highest crime regions of the city are and to focus their policing patrols on those areas. And that has had an extraordinary impact on the crime rate in New York City over the last 15 or 20 years. And then there's a good example in Singapore where they use real-time road pricing in order to better control and make more efficient the traffic flow in that city. So you start to think a little bit about what the potential is here. You realize there are many different dimensions in which you can apply this thinking, not only to minimize or make more efficient energy use, which is where I started, but to improve the efficiency, resilience, livability of cities. So I think that's pretty much everything I wanted to say. I hope I've stretched your mind a little bit, and as I said at the beginning, would be very grateful for your comments and feedback. Thanks very much.
The talk is open for questions, please. Please use the microphone.
It was very interesting to hear your data analysis or what you want to do with it. We, of course, also know the secret surveillance methods of the United States, which is also of an interesting side. but that is a special tension, which is another theme. But I think also manipulation is not on the screen if you think only on mass data in this way. We are also misled in the last decades, for example, oil addicted by the industry and oligopoles. And in such circumstances, I think we have also to think about the development of elites we have in sciences and in governments which are depending on networks. And the question is how in which circumstances can we think freely enough and decide freely? I think we couldn't do, and that's a reason of the crisis we see will coming up, and we can't act because of this interdependency.
Yeah.
Thanks.
You raised several different really interesting issues. Let me come to the interdependency first, of course. I mean, the energy system is a system. The generation has to work with the transmission and the loads. The fuels have to work with the vehicles and the filling stations and so on. And that's another aspect that makes things change slowly. My own inclination as a scientist is that a way to help society get to a better place is to make the understanding and the information available to people. That's not always the way other institutions want to do it, but I think as one goes about this, we should try to be as public and as open about the data. Although, of course, you know, sometimes in the political dialogue, the facts don't always matter. And unfortunately, that's something we have to deal with. But that's a different problem. That's education.
I lived in Washington for quite a while, and you showed a nice picture of the, yeah, it wasn't Washington, it was New York skyline at night. One could show this of many other places and knows since many years actually that there are not only buildings lit from the outside, but really that they waste a lot of energy through the buildings.
Yeah.
So it's these data have been there for many years, and actually you do not have to collect when you know you have just a one pane window, that this is not the best insulation, and there have been other things around for decades. So why are you so optimistic that things will change just with the new data collection?
Yeah. I think, so the picture I actually showed was in the infrared, although you can see pictures, of course, in the visible that show who's keeping the lights on and so on. You know, at one level, if you could put pictures like that up in real time, you might, I'll use the word, not shame, but induce people to take action. Also, I've got that kind of data, and I can start to correlate it with other data. What goes on in that building, when is it occupied, when is it not occupied, and so on. You can perhaps start to tease apart which people are using energy, if you like, in an efficient way, and which people are not. So my general sense is more data, more understanding will help us target better some of the changes we'd like to see happen. Of course, buildings are relatively static. The traffic, of course, is changing much more frequently.
I was curious about what your opinion is on the accountability of all this data. So who's going to be accountable for this? How do we know that this data is not going to fall into the hands of some companies who have monopolistic measures and those sort of issues? Like, yeah, who's in charge here of all this data?
Yeah, the answer is nobody at the moment. I think the commercial entities are doing an amazing job of collecting and correlating data, targeted advertising, other things like that. I guess what the point here is that beyond commercial means, that there are legitimate and interesting government uses to try to make things run more efficiently. The general issue of who's got control of data, what the strictures are, you know, brave new world. We've not thought about this very hard right now. Yeah. Very good question.
Coming back to your wonderful picture, this infrared picture. So this, you address the issue of energy efficiency, and we carried out a similar project a couple of years ago with the city of Cologne, where you stay overnight. So you will see some of our results and can experience them. The cooperation was with the local utility, Rhein Energie, and we address the issue of energy efficiency of the individual buildings at the level of the ownership. So we had all the information available and processed them with a geographical information system, and we could identify those buildings being above average with respect to energy efficiency and those below, and we could address this at the individual owner level. So we knew who is responsible for wasting energy. And then the issue came up after having done this wonderful and beautiful study. What shall we do with the results? And this became a very hot potato, I can tell you, because all these individual issues popped up, and the provider or those who paid for the study, they were not aware that this could happen. And let me say, from this study, we could conclude that in most cities and most buildings, you find that the energy efficiency, the insulation level, is much below prescribed standards. So, and again, the question is, what do you do with these results? Do you set up a kind of police saying, well, look, we have found out that you are wasting energy? And then this social issue comes up. If you force owners to renovate their buildings, how will they go and recapitalize all these measures, bringing higher payments from the local people? So this is a real hot potato. So, and that's what we have done. We have some experience in that.
I'd like to hear more about that. It sounds highly relevant. Yeah, right. hot houses. Right.
An interesting data set to have, I don't know if it exists, would be the global availability of oil. Do you consider, especially in your former functions as a worker at BP and at the Department of Energy, to that we have already reached global peak oil?
Do we have a minute or two to do the peak oil discussion?
It's interesting.
So let me just say, I do about 2 energy talks a week, and I've been doing so for about 5 or 6 years, and I think I've heard just about every question that anybody's ever asked, although now I'm talking about a new topic. Of course, I'm getting new questions. Anyway, peak oil, I've got the answer for, if you like, all right? It depends what you mean by oil, okay? There are abundant hydrocarbon reserves in the ground that can be accessed with today's technologies. Give you a sense of the numbers, and sorry I didn't put in here an oil supply curve. The world has used 1 trillion barrels of oil since we started producing oil 150 years ago. In the next 25 years, it will need another 1 trillion barrels of oil. There are, if you count conventional oil, enhanced oil recovery, offshore, Arctic, are small pieces, but the biggest pieces are shale oil, tight oil as it's called, bitumen, heavy, very heavy oil, and those amount to about 5 trillion barrels yet to be extracted. The costs are somewhat higher. Costs today are pretty cheap, $10, $15 a barrel for easy oil, $50 a barrel offshore. You can still make money at a $100 price at $50 a barrel. It goes up to about $70, $80 a barrel for the shale oil. But nevertheless, there's plenty in the ground. It's a question of economics and technology about what gets extracted. Okay, very good.
Yeah, I think thanks to the speaker again. Thank you very much.